Welcome to our sixth lecture. This week we're going to finish talking about second and higher order differential equations. We're going to start by solving some initial value problems. We will be using the ideas from the last 2 weeks. So partly the first section will be revision of the last 2 weeks. Then we will look at another method to find a particular solution, which is called the method of variation of parameters. And then in the final section of today's lesson, we're going to be extending the ideas from second order equations to higher order equations. First, let's solve some initial value problems. Let me remind you that if we want to solve a problem like this, that's a linear second order non-homogeneous differential equation with constant coefficients and 2 initial conditions. The method is as follows. The first thing we want to do is we want to find the general solution to the corresponding homogeneous equation. We also need to find a particular solution to the non-homogeneous solution. If our function gt does not solve the homogeneous equation, then we would expect our ansatz, our mathematical guess, to look like g of t. So if g of t is an exponential function, we're going to use the same exponential function in our ansatz, just with different numbers in. If it's a cos function, we'd expect to also have a cos function, but anytime we have cos, we also have to have sine as well, and so on. However, there's a difficulty which may occur. If gt does solve the homogeneous equation, then we can't use the same type of functions in our particular solution. So what we do is we multiply it by t and repeat as necessary. Step 3 is we add these 2 functions together. The general solution to the homogeneous equation plus a particular solution to the non-homogeneous equation gives us the general solution to the non-homogeneous equation. And then finally in step 4, we find the constants in the general solution, the C1 and C2, so that we can satisfy the initial conditions. Now, let me just point out a mistake which we often see students making in exams. You must do step 4 last. First, we need to get the general solution to the non-homogeneous equation, and then finally, we try to find the 2 constants. If you try to find the 2 constants earlier, then you might get the wrong answer. To show this, I'm going to solve this simple problem. Y double prime minus y is equal to 2 e to the power t with the initial conditions y of 0 is 1, y prime of 0 is 2. And I'm going to solve this 2 ways. I'm going to solve it the correct way first, and then I'm going to solve it the wrong way by doing the steps in the wrong order. First thing we do, step 1, we need to find the general solution to the homogeneous equation. So we write down the characteristic equation, r squared minus 1 is equal to 0. We find that the roots are 1 and minus 1, and then we can write down that the general solution is c1 e to the power t plus c2 e to the power minus t. Step 2. Next, we need a particular solution to the non-homogeneous equation. Now, note here that a e to the power t solves the homogeneous equation. So we can't use exactly the same function in our ansatz. Instead, we need to multiply it by t. So the ansatz we're going to be trying is going to be a constant a t e to the power t. Differentiate this 2 times. Substitute this into the differential equation and simplify. And what we find is we need to have 2e to the t equal to 2a e to the power t. So of course a is equal to 1, and we found our particular solution, t e to the power t. Step 3, add them together. C1 e to the power t plus C2 e to the power minus t. We found that that is the general solution to the homogeneous equation. And then we do plus the particular solution to the non-homogeneous equation. Now we have the general solution to our non-homogeneous differential equation. And the final step, step 4, is to find the constants C1 and C2, which satisfy the initial conditions. And I will leave it for you to check that for this example, we want C1 equal to 1 and C2 equal to 0. So the correct solution to this initial value problem is going to be y is equal to e to the power t plus t e to the power t. Okay. Now I've put that at the top. This is the correct solution. Now let's do this wrong. Somewhere in this solution is going to be a mistake. Again, I'm doing step 1, and this is just a copy and paste of the previous step 1. This is all fine. This is correct. After step 1, I'm going to do step 4. I'm going to find constant C1 and C2, which satisfy the initial conditions. And again, I'll leave this for you to check. This time I found 3 over 2 and minus a half. So far I've got 3 over 2 e to the power t minus a half e to the power minus t. After step 4, I'm going to do step 2. Find a particular solution to the non-homogeneous. This is a copy and paste from the previous slide. This is all exactly the same as we did before. Just as we did before, we get the particular solution t e to the power t. Add the two solutions together, and we get 3 over 2 e to the power t minus a half e to the power minus t plus t e to the power t, which is wrong. Now that we've done plus t e to the power t, it doesn't satisfy the initial conditions anymore. It's wrong because I found the constant C1 and C2 too early. That needs to be the final step. First, we need to get the general solution to the non-homogeneous equation, and then only in step 4 can we find the constants. Let's do another question. Solve minus y double prime plus 6y prime minus 16y is equal to 1 plus 6 e to the power 3t sine 2t with the initial conditions. Y of 0 is 15 over 16. Y prime of 0 is minus 1. This is an exam question which I used for a slightly different course back in 2013. And back in 2013, it was a 2-hour exam with 4 questions. So really, this was a 30-minute question. So ask yourself, could you solve a question like this in 30 minutes or less? To solve this differential equation, to find the general solution to this differential equation, we're instead going to be looking at 3 easier differential equations, a green one, an orange one, and a blue one. The green one is the corresponding homogeneous equation. In the orange equation, I'm just looking at the first part of GT. I'm just looking at the 1. And in the blue equation, I'm just looking at the second function of G. I'm going to be looking at these 3 differential equations separately, and then I'm going to be adding their solutions together. So first the homogeneous equation, first the green equation. What do? We write down the characteristic equation. Minus r squared plus 16r minus 16 equal to 0. And I'll leave it for you to check that the roots are 3 plus or minus I root 7. As soon as we know the roots, we know that the general solution is constant e to the power 3t sine root 7t plus constant e to the power 3t cos root 7t. And it doesn't matter which, out of sine and cos, it doesn't matter which one we write first and which one we write second, as long as we have them both in our answer. Let's move on to the orange equation. We need a particular solution to this equation. The function here, g, is just a constant. So the ansatz we try is just going to be a constant. Put this in, and we find that the constant must be minus 1 over 16. So we have our particular solution. Our particular solution is minus 1 over 16. That leaves one equation left. We still need to look at the blue equation. What function do we have here? We have an exponential function multiplied by a sine function. So our ansatz is going to be an exponential function multiplied by a sine function. E to the power 3t sine 2t does not solve the homogeneous equation, so we can use this in our ansatz. So we expect to have a constant e to the power 3t sine 2t, and any time that we have a sine, we also need to have a cos term. So constant e to the power 3t cos 2t plus constant e to the power 3t sine 2t. Differentiate this 2 times and substitute it into the differential equation and simplify. We end up with e to the power 3t cos 2t multiplied by minus 5a plus e to the power 3t sine 2t multiplied by minus 3b on the right. And we need this to be the same as 6 e to the power 3t sine 2t for all t. So now we know what values of a and b to choose. We're going to need a equal to 0 and b equal to minus 2. And that gives us our particular solution to the blue equation. Now that we have these, we can add them together. Adding these 3 solutions together, that's green plus orange plus blue, we find the general solution to the differential equation. There's one step left, always the final step. Find the constants C1 and C2. The first condition, 15 over 16 equal to y over 0, tells us that we must have C2 equal to 1. Differentiate it and then set t equal to 0, and we find that we must have C1 equal to 0. I'll skip past this. I'll leave this for you to check later. And that's what we need to do. Therefore, the solution to the initial value problem is going to be e to the power 3t cos root 7t minus 1 over 16 minus 2e to the power 3t sine 2t. Ask yourself if you could solve a problem like this in 20 or 30 minutes. Okay, so we've been using the method of undetermined coefficients. And this method works well if GT is a nice function or a sum of nice functions. E to the power kt, sine kt, a polynomial, e to the power at cos kt. These are all nice functions. You can all guess what to do, what ansatz to do. We can guess what ansatz to use if we have a nice function. But if GT is not a nice function, then we might need to use a different method to find a particular solution. If we have a complicated function for GT, then we're going to need the method of variation of parameters. For example, find a particular solution to y double prime plus 4y is equal to 3 cosec t. Cosec you might be familiar as writing CSC. This is also a standard way to write it. For this GT, we can't use the method of undetermined coefficients. So what can we do? The idea is this. We know that we can easily find that the general solution to the homogeneous equation y double prime plus 4y equal to 0 is c1 cos 2t plus c2 sin 2t. So the idea is we're going to try to replace the constant c1 and c2 by some function u1 and u2 that we don't know yet. And then we're going to try to find u1 and u2 such that capital Y solves 2. If we can do that, then we have our particular solution. A key idea here is that there's going to be infinitely many particular solutions. There are going to be infinitely many choices of u1 and u2 that we can use. And we only need to find one particular solution. We don't need to find every particular solution. So we just need to find one u1 and one u2 which works. That means we can add in an extra condition whenever we want. Anytime it's going to make our calculation easier, we can add in one extra condition. So let's do this. Let's suppose that our particular solution is u1 cos 2t plus u2 sin 2t. Differentiate it. We get u1 prime cos 2t minus 2u1 sin 2t plus u2 prime sin 2t plus 2u2 cos 2t by the product rule. Now, this is already starting to get complicated. Already we have 4 terms here. Let's take our chance to make this easier. Let's use our chance to add a condition here. Let's suppose we want to say that the red terms are equal to 0. If we can assume this, then it makes our y prime easier. Now our y prime only has 2 terms, and when we differentiate it, we have y double prime with 4 terms in. That's manageable. We can do that. Okay, and then put into the differential equation 3 cosec t. We want to be equal to capital Y double prime plus 4 capital Y. And that simplifies to minus 2 u1 prime sin 2t plus 2 u2 prime cos 2t. Which is a little bit complicated, but not too complicated. So what do we have? Let's summarize this. We're trying to find u1 and u2 which satisfy 2 equations. This green equation we've just found, and we also want to find u1 and u2 which satisfy this red extra condition that we used before. Can we find u1 and u2 which satisfy these 2 equations? Now, this is a linear system of 2 equations for u1 prime and u2 prime. We know how to solve linear systems from linear algebra. For example, take the second equation, rearrange it. u2 prime must be minus u1 prime cos 2t over sin 2t, and then substitute this into the first equation. On the left, we still have 3 cosec t. On the right, the first term stays the same, minus 2 u1 prime sin 2t, plus 2. Instead of u2 prime, I'm writing minus u1 prime cos 2t over sin 2t, and then multiplied by cos 2t. We can simplify this. Simplify this and then rearrange. We find that we need to have u1 prime is minus 3 cosec t sin 2t over 2. And that simplifies further, because cosec means 1 divided by sine, to minus 3 cos t. Check it. And then after we know u1 prime, we can find u2 prime. We don't want u1 prime and u2 prime, we want u1 and u2. So what we do is we integrate. u1 is the integral of u1 prime. Integral of minus 3 cos t is minus 3 sine t. Don't need to worry about a constant, remember, because we're only trying to find one u1 which works. And u2 will be the integral of 3 over 2 cosec t minus 3 sine t. And that is 3 over 2 natural log of the absolute value of cosec t minus cotan t plus 3 cos t. And then we have all that we need. Our particular solution is going to be u1 cos 2t plus u2 sin 2t. Now we know u1 and u2. Put them in, simplify a little bit, and we get our particular solution. It's this complicated function at the bottom. 3 sine t plus 3 over 2 natural log absolute value of cosec t minus cotan t sine 2t. So yes, this is a little bit complicated. It's complicated perhaps because of all the calculation here. Let's just summarize what I was doing here. Suppose we know that c1y1 plus c2y2 is the general solution of L of y is equal to 0. Step 1, we're going to guess that our particular solution is equal to u1y1 plus u2y2. We're going to replace the constants by functions. In order to make our calculation a little bit easier, we're going to make an extra condition. And the extra condition is always the same condition. It's always u1 prime y1 plus u2 prime y2 is equal to 0. We're going to put capital Y into the differential equation using the extra condition to make our calculation a little bit easier. And we're going to find an equation for u1 prime and u2 prime. In fact, we end up with two equations. We end up with the extra condition and then the new equation that we find. Solve these two equations to find u1 prime and u2 prime, and then integrate. As soon as we know u1 and u2, we know a particular solution to the non-homogeneous differential equation. Let's do another example. Find a particular solution to y double prime minus 2y prime plus y is equal to e to the power t natural logarithm of t. And again, we have something complicated here. E to the power t is a nice function. If we just had e to the power t, we would use the method of undetermined coefficients. But natural logarithm is not a nice, easy function. Natural logarithm is a complicated function. So this time, we have to use the method of variation of parameters. First, we need the general solution to the homogeneous equation. So using the characteristic equation, we find that the roots are 1 and 1. So the general solution to the homogeneous equation must be c1 e to the power t plus c2 t e to the power t. We're going to replace c1 and c2 by the unknown functions u1 of t and u2 of t. And then we make the extra condition. And as I said on a previous slide, the extra condition is always the same. It's always u1 prime y1 plus u2 prime y2 is equal to 0. And for this particular example, because y1 is e to the power t, and y2 is t e to the power t. The extra condition that we're going to be using is that y1 prime plus y2 prime t is equal to 0. Right. Now we can do our calculation. I need to differentiate capital Y 2 times and then put into the differential equation and see what I get. Differentiate y1 time, we get u1 prime e to the power t plus u1 e to the power t plus u2 prime t e to the power t plus u2 e to the power t plus u2 t e to the power t. But remember, we have this extra condition. So two of these terms we can remove. And we just get that y prime is u1 e to the power t plus so u1 e to the power t plus u2 e to the power t plus u2 t e to the power t. Differentiate this again. And then we can use the extra condition again. Remember, u1 prime plus u2 prime t is equal to 0. So these two terms are going to disappear. We're left with y double prime is u1 e to the power t plus u1 e to the power t plus u2 prime e to the power t plus 2u2 e to the power t plus u2 t e to the power t. Okay, these are going to go into the differential equation. And then we're going to want to simplify this as much as we can. What can we simplify here? Let's see, there's a u1 e to the power t minus 2u1 e to the power t, and then plus u1 e to the power t. Those are going to cancel out. There's a 2u2 et here, and then a minus 2u2 et just here. Those are going to cancel. u2 t e to the power t, another u2 t e to the power t, and then minus 2 u2 t e to the power t. Again, those will cancel. And what are we left with? We're left with just u2 prime e to the power t. Oh, we can go even further. Look, e to the power t will cancel with e to the power t. So what do we know? We know that u2 prime is natural logarithm of t, and therefore u1 prime must be minus u2 prime t, or minus t ln t. Now that we know u1 prime and u2 prime, we can integrate them to get u1 and u2. So here we go. The integral of minus t ln t is minus a half t squared ln t plus a quarter t squared. And the integral of ln t is t ln t minus t. Check them, please. Now that we know u1 and u2, we know our particular solution. Okay, great. So that's how we do the method of variation of parameters. Isn't there an easier way? And the answer is yes. Still, we would have to do the same calculations, but there's an easier way to think about this, an easier way to remember this perhaps. Suppose that we know y1 and y2 form a fundamental set of solutions of this homogeneous equation. Then we can find a particular solution of this non-homogeneous equation using this formula. It's minus y1 integral of y2g over w plus y2 integral of y1g over w, where w is the Wronskian of y1 and y2. If you want to, just remember this formula in case you're given a method of variation of parameters question. Okay, now before I go on, there's a question I'm often asked at this point, and that's, does it matter which function we call y1 and which function we call y2? I think students are noticing that there's a minus sign in front of the first one and there's a plus sign in front of the second one. And they're wondering, well, what happens if we swap places of y1 and y2? Don't we get minus the answer? And the answer is no, because if we swap the functions in the Wronskian, that's the same as swapping two columns in the determinant of a 2 by 2 matrix. And what happens to the determinant if we swap two columns in a matrix? We multiply the determinant by minus 1. So then we get minus 1 multiplied by minus 1, which is plus 1. So the answer is no. It doesn't matter which function you call y1, and it doesn't matter which function you call y2. You'll always end up with the same particular solution. So, for example, find a particular solution to y double prime minus 2y prime plus y is equal to e to the power t ln t. This is the example that we just did, but now we're going to solve this using the theorem. First, we need a fundamental set of solutions to the homogeneous equation. So we write down the characteristic equation, we find the roots, and then we find that e to the power t and t e to the power t form a fundamental set of solutions to the homogeneous equation. And then we need the Wronskian of these two functions. So W is the determinant of the 2 by 2 matrix, y1, y2, y1 prime, y2 prime. And I'll leave it for you to check that the Wronskian of these two functions is e to the power 2t. Okay, so let's recap what we know. At the top, we have our two functions, y1 and y2. G from the differential equation was e to the power t ln t, and we know that the Wronskian is e to the power 2t. Now we're ready to do our calculation. We're ready to substitute these functions into the formula. So here we go. Minus e to the t, integral of t e to the power t, e to the power t ln t, over e to the power 2t dt, plus t e to the power t, integral of e to the power t, e to the power t ln t over e to the power 2t dt. Some of these terms are going to cancel. E to the power t, e to the power t will cancel with e to the power 2t, and also over here. E to the power t, e to the power t will cancel with e to the power 2t. So what do we have? We have to calculate two integrals, the integral of t ln t and the integral of ln t. That's exactly the same two integrals that we had to calculate using the previous method. Ultimately, we're doing the same amount of work using this method, but perhaps it's easier to understand what we're doing if we just start straight away with the formula. So we calculate these two integrals, and then we simplify. And you can check that we get exactly the same solution exactly the same particular solution that we got using the previous method. It's completely up to you which method you use. You can either use this formula or you can use the previous method where you start with the guess that the solution is u1 y1 plus u2 y2. The final topic for today's lesson is higher order linear differential equations. What we're going to do is we're going to take the ideas from the previous weeks, from the last 2 weeks and today's lesson, and we're going to extend them to higher order linear differential equations. So for example, the first problem I want to solve is 4 derivatives of y plus y triple prime minus 7y double prime minus y prime plus 6y is equal to 0 with these initial conditions. This is a fourth order differential equation, so we need to have 4 initial conditions. The number of initial conditions is always going to be the same as the order of the differential equation. So what do? The first thing we do is we write down the characteristic equation. First, in the differential equation, we had y 4 derivatives. So in the characteristic equation, we're going to start with r to the power 4. And then we had y triple prime, so in our characteristic equation, plus r cubed. And then minus 7y double prime, so minus 7r squared, etc. Exactly the same ideas as for second order linear equations. And I'll just tell you that this characteristic equation has roots 1, minus 1, 2, and minus 3. As soon as we know the roots, we can write down the general solution to the differential equation. Constant e to the power t plus constant e to the power minus t plus constant e to the power 2t plus constant e to the power minus 3t. So exactly the same ideas for second order equations. There's nothing new here except that we have more terms here. For a fourth order equation, we need to have 4 linearly independent solutions. Our fundamental set of solutions will include 4 different functions. Then we need to find the constant. So we start with the initial conditions. Set t equal to 0, solve this linear system to find the constants. Yes, it's more work, but there's nothing new here. And then we can write down the answer. Exactly the same ideas as from before. Solve y triple prime minus 4y double prime plus 2y prime plus 3y is equal to 0. For this differential equation, the characteristic equation is r cubed minus 4r squared plus 2r plus 3 is equal to 0. How can we solve this characteristic equation? How can we solve the third or higher order characteristic equation? Well, one way, and perhaps the easiest way if you were given an exam question like this, is to think our teacher probably gave us an easier one. So at least one of the roots is going to be one of the easy numbers. 0, plus 1, minus 1, plus 2, minus 2, plus 3, minus 3, plus 4, minus 4, etc. Probably one of these easy numbers is going to be a root. So let's try them. Does r equal to 0 work? Let's try it. 0 cubed minus 4 times 0 squared plus 2 times 0 plus 3 is equal to 3. It's not equal to 0. No. Let's try again. What about r equal to 1? Does that work? 1 cubed minus 4 1 squared plus 2 times 1 plus 3 is not 0. No, doesn't work. Let's try again. What about minus 1? Does that work? No. Let's go to the next number. What about plus 2? Does that work? No. Does minus 2 work? No. Does 3 work? Yes. 3 works. 3 cubed minus 4 times 3 squared plus 2 times 3 plus 3 is equal to 0. So one of the roots must be 3. That tells us that we could write our characteristic equation as r minus 3 multiplied by a quadratic equation. What is the quadratic equation? Let's try it. Let's multiply this out. I get r cubed plus b minus 3r squared plus c minus 3b r minus 3c. And that needs to be the same as r cubed minus 4r squared plus 2r plus 3. So b must be minus 1 and c must be minus 1 as well. Let's quickly check the middle one. C minus 3b, that's minus 1 minus 3 times minus 1, or minus 1 plus 3, minus 1 plus 3 is 2. Yes, that works. So our characteristic equation is r minus 3 multiplied by r squared minus r minus 1. And you know how to solve a quadratic equation. That's straightforward. I'll just tell you that the roots of this characteristic equation are therefore 3, a half plus root 5 over 2, and a half minus root 5 over 2. It's reasonable to guess that if you were given a question like this in an exam, then at least one of the roots would be an easy number. Maybe all 3 are easy numbers, but at least one of them must be an easy number. I'm not going to finish this example. I'm going to leave this for you to finish. Now that you know the roots, you could write down the general solution to this differential equation. Let's do another one. Solve 4 derivatives of y minus y is equal to e to the power of t. Step 1, we're going to find the general solution of the homogeneous equation. Step 2, we're going to find a particular solution to this differential equation using the method of undetermined coefficients. And then step 3, we're going to add those 2 functions together. So first, we take the characteristic equation. 0 is equal to r to the power 4 minus 1, or r squared minus 1, r squared plus 1. The roots of 1, minus 1, I, and minus I. Now that we know these 4 roots, we can write down the general solution to the homogeneous equation. From r equal to 1, we get the function e to the power t. From r2 equal to -1, we get the function e to the power minus t. And from I and minus I, we're going to get the functions cos t and sin t. These four functions are linearly independent. The general solution will be a linear combination of these four functions. Okay, great. That's the homogeneous equation taken care of. Next, we need to find a particular solution to the non-homogeneous differential equation. What ansatz are we going to try? Because e to the power t solves the homogeneous equation, we can't use e to the power t. So instead, we're going to multiply it by t, and we're going to try the ansatz constant t e to the power t. We need to differentiate this 4 times. Here we are. And then we're going to put these into the differential equation. E to the power t must be the same as 4a e to the power t, so a must be a quarter. So we have our particular solution. Our particular solution must be a quarter t e to the power t. Again, there's nothing new here. We're just using the same ideas as from second order equation. Yes, there's more work here because we need to do 4 derivatives instead of 2 derivatives, but there's no new ideas here. So we have our general solution to the homogeneous equation. We have our particular solution to a non-homogeneous equation. We add them together. The general solution to the differential equation is therefore c1 e to the power t plus c2 e to the power minus t plus c3 cos t plus c4 sin t, and then plus a quarter t e to the power t. What do we do with repeated roots of the characteristic equation? The answer is we just multiply by t. So for example, let's suppose you had some differential equation, a 6th order differential equation, and let's suppose that the roots of the characteristic equation are 7, 7, 7, 7, 7, and 8. What is the general solution? For the first root is 7, we would just have e to the power 70. Then we have 7 repeated. We need another function. We multiply it by t, and we get t e to the power 70. The third root is also 7. We need another function, so we multiply by t again. Our third function is going to be t squared e to the power 70. And so on. For the fourth root, I have t cubed e to the power 70, and for the fifth root, t to the power 4 e to the power 70. The sixth root is a different number. The sixth root is 8. We know what to do with 8. We just have e to the power 8t. So in summary, if you have repeated roots, just keep multiplying by t. And then we come to the final example of today's lesson. Here's an example of which I'm calling going backwards. Find a linear, homogeneous differential equation with constant coefficients, which has the general solution this. Now, this is a different type of question. This time we're given the solution and we're asked to find a differential equation which has this solution. There's actually infinitely many correct answers to this question. We just need to find one correct answer. So what can we say here? What are the roots of the characteristic equation going to be? Let's look at the first two terms. That's c1 e to the power t plus c2 t e to the power t. They both correspond to the root r equal to 1. And then let's look at the last four terms. Those are all e to the power 2t, and then sine t or cos t or t sine t or t cos t. These all correspond to 2 plus I or 2 minus I. So our characteristic equation is going to look like this. We have root 1, but we have two of them, so we're going to have r minus 1 squared. We can have 2 plus I, so r minus 2 minus I, and this is repeated, so again this is going to be squared. Then we have r is equal to 2 minus I. That gives us the bracket r minus 2 plus I. And again, this is a repeated root, so this is squared. Multiply all of these out, and we get the characteristic polynomial r to the power 6 minus 10 r to the power 5 plus 43 r to the power 4 minus 100 r cubed plus 131 r squared minus 90 r plus 25. What I've done is I've looked at what must the roots be. The roots are 1, 1, 2 plus I, 2 plus I, 2 minus I, 2 minus I. And then I've seen that this must be the characteristic equation. We need to write down a linear homogeneous differential equation which has this characteristic equation. But now that's easy. Instead of r to the power 6, we'll just have 6 derivatives of y. Instead of r to the power 5, we'll just have 5 derivatives of y. This is a differential equation which has the general solution given in the example. And that is the end of this week's lesson. Next week, we're going to start on chapter 4. We're going to start talking about the Laplace transform and how it can be used to solve some initial value problems. Now I'm ready to answer your questions. What is the syllabus of the midterm exam? It's chapters 1, 2, and 3. If you registered after the 1st of November, then you have a choice. You could either take the first midterm exam, or you can apply to the Dean's office and ask to take the makeup exam. If you look in the announcements that I made, I gave the announcement that the Dean made. I also listed the application form that you would need to fill in if you want to apply to the Dean's office for a makeup exam. The exams are all face-to-face exams. The makeup exam hasn't been arranged yet. It will be towards the end of term. I'm guessing that it will be in the 13th week of term, but I don't know for certain yet. We'll announce it nearer the time. Yes, the makeup exam will be the same syllabus. Don't worry about the points you're given for the attendance. The OLearn system is unreliable. There is no homework for this course. I meant to write, don't worry about what OLearn says your attendance is unreliable. I made an announcement about this. If it's not listing the correct attendance for you, then just tell me at the end of term. There is no required